Let's take a look at the next topic in section 4.1, and that's the natural exponential function. So, an exponential function, recall from the previous video, is a function of the form f of x equals b to the x, where b is any real number bigger than 0, different from 1. So the number b is called the base of the exponential function. So we want to understand the natural exponential function. And this is the function whose base is the number e. So this number is the value that the expression 1 plus 1 over n to the nth power approaches as n gets larger and larger and larger. So when n is 1, 1 plus 1 over 1 to the first is 2. When n is 2, 1 plus 1 over 2 to the second is 2.35. Similarly, when I let n equal 10, and then 100, and then 1,000, 10,000, 100,000, a million, 10 million, and 100 million, I see that I'm making large changes in the value of n, and I'm getting very small changes in the value of 1 plus 1 over n to the nth. The value that this approaches is called e, the natural base. So e is approximately 2.718. Notice this irrational number has a decimal form that never ends or repeats. So I could never finish writing the number e. But notice this value that we see at the bottom of the chart, where n is 100 million, is only an approximation of the value of e. So the natural exponential function is f of x equals e to the x. So now e, which is approximately 2.718, is the base of my natural exponential function, whose domain is still all the real numbers. The range is all positive real numbers. The y-intercept is 1. E to the x goes to infinity as x goes to infinity. E to the x goes to 0 as x goes to negative infinity. The x-axis, whose equation is y equals 0, is the horizontal asymptote, and the function is 1 to 1. All the characteristics of a function which is exponential with a base bigger than 1. Now, one of the most commonly used forms of this exponential function is used when I'm continuously compounding interest. A, the accumulated value, equals P e to the RT. P is the principal, R is the interest rate per year, T is the number of years. Let's look at an example of this where S equals C times 1 plus R to the T. And notice C is the value today. R is the inflation rate. S is the inflated value T years from now. And T is, of course, the number of years. So notice that in this problem, I want to find the value of a house in 5 years, whose current value is $510,000, where the inflation rate is 3%. So I'm trying to find S of this function, where C is 510,000 and R is 0.03. Remember, I have to write the interest rate as a decimal, and my time is 5. So I simply am replacing C, R, and T with the given values, and I'm finding S. So S is 510,000 times 1 plus R, 1 plus 0.03 to the 5th power. So this is 510,000 times 1.03 to the 5th. And I use my calculator to get an approximation of this. And I find that the calculator allows me to conclude that it will be worth $591,230. So in 5 years, the house will be worth $591,230 when currently it's only worth $510,000. Let's look at this problem where we want to find the accumulated value of an investment of $5,000 for 10 years at a rate of 6.5% if the money is compounded semi-annually, quarterly, monthly, and finally continuously. So for the first 3 parts of this problem, we use the formula A equals P times 1 plus R over N to the NT, where P is 5,000, T is 10, R is 0.065, and N depends on how many times I'm compounding a year. So for part A, N is 2. To compound semi-annually means to compound twice a year. So A is 5,000 times 1 plus 0.065 over 2 raised to the 2 times 10 power. And I use my calculator to find the value of this calculation. So my accumulated value, if I only compound twice a year, is about $9,479.19. Now, if I compound quarterly, I'm compounding 4 times a year. So N is 4. And I use the same formula, replacing 2 with my N value of 4. So wherever I have N in the formula, I have a 4. And using the calculator, I approximate this value at $9,527.79. Now for part C, I'm compounding monthly. So that means I'm going to compound 12 times a year. So my N value is 12. I use the same formula. P, the principal, is 5,000. R, the interest rate, is 0.065. T is still 10, but now N is 12. And using my calculator, I'm able to approximate this value at $9,560.92. Now when I get to part D of the problem, I'm using a completely different formula. Now accumulated value A, or the amount at the end of the time period, is P e to the RT. So 5,000 times E to the 0.065 times 10. And I use my calculators natural exponential button. So the base of E is programmed into the calculator, and I simply am putting in the value of the exponent, which is 0.65. When I multiply 0.065 times 10, I get approximately $9,577.70. So obviously, the larger the number of compoundings, if all other things remain the same, the more the accumulated value is. So I get the largest accumulated value when I compound continuously. So this means every moment the interest is being compounded.